I'm going to show you how we can use the principle of conservation of momentum and the conservation of kinetic energy for elastic collisions to derive another equation which is very useful. So let's get started with a diagram. One mass and a second mass, so that's a large m, lowercase m. Initially, the two masses are moving towards each other with UA and UB. After the elastic collisions, this is only for elastic collisions, then our two masses are now moving away. And they do so with VA and VB. Okay. Let's apply the principle of conservation of momentum to this. In order to do so correctly, we're going to need to define which way is positive, which way is negative, because we have two velocities moving in opposite directions, two velocities in opposite directions. So usually we take to the right as positive, so we'll do that in this case. So conservation of momentum. The initial momentum, MUA minus MUB. It's equal to the total final momentum, so total initial equals total final. We've got this moving in the negative direction, so this is minus MVA and plus MVB. Okay, now let's get our M terms together, so our A and B terms. We have MUA. What I'll do is I'll just write it out with the brackets. So it's MUA plus VA is equal to little m UB plus VB. Okay. That's equation 1. So we've got our A and B terms together. Conservation of kinetic energy now, so similar principle, but here kinetic energy, scalar quantity, is not affected by positive or negative, so that will be different. So firstly for this one, this is UA squared plus a half MUB squared, and then I'll do the other two terms is equal to the final ones. Right, every term there has a half, so they will cancel out. And similarly to what we did here, when we grouped our A and B terms, let's group the A and B terms. Okay, so we've got the VA has come over to this side, VA squared, or the MVA squared rather, and the MUB squared has gone over to this side. That's the negatives there. Okay. So what can we do with these equations now? Well, the first thing is we're going to take equation 2, and if you notice, we can expand those brackets out into factors. So let's do that. Firstly, so we get m times, so this would become, if I multiply UA plus VA by UA minus VA. So UA plus VA multiplied by UA minus VA, then I would get that term there. So that's the left-hand side of the equation. Similar procedure here, but notice that here we have UA minus VA squared, and here we have VB minus UB terms being squared. So that's a slight difference there. We have UB plus VB. So that's what we can do with equation 2. Now notice from equation 1 that M UA plus VA is this term here. Is equal to M UB plus VB. That term there. Those two terms are equal. So if we divide both sides of the equation by MUB plus VB, then this side, that term divided by itself will become 1, but so will this, because it's equal to that term. If we divide that by that term, then it will be equal to 1 as well. So now what do we have? We have an expression that says UA minus VA is equal to VB minus UB. And then final step, let's have the U terms together and the V terms together. So UA plus UB is equal to and then we have it. So that's another equation that we can use for elastic collisions. The sum of the initial velocities is equal to the sum of the final velocities. And that only applies to elastic collisions. It does not apply to inelastic collisions because the kinetic energy of an inelastic collision is not conserved. So we can't use that equation, and therefore we can't arrive with that final equation there.